In this lecture, we will solve some circuits using S-domain techniques. This is our first example, where we're told that the circuit that I'm about to draw is in steady state. Okay, at t equals 0 minus, and at t equals 0 we have a switch that changes position. Now the circuit is as follows. Another resistor, source, and the capacitor. Okay. The sources are constant. Here we have 10 volts, and here we have 5 amps, 2 Henry, 1 ohm, 2 ohms, 1/4 farad inductor current IL, and this is how we label the capacitor voltage. Now, the switch moves from the bottom position to top position at t equals 0. Okay, so what happens is at t equals 0, you remove this 5 amp current source. And then what remains is the circuit that that appears below this line, okay, here. So what we have to figure out is we are asked for find VCT for T positive, okay, so after the switch moves to the top position. Okay, so what we do is we take this circuit and we transform the circuit after the switch moves to the top position. We take the circuit and move it to S-domain. Okay, for that we need to know the initial conditions of the dynamic components, which are not given, so we have to figure out. Okay, so it's in a sense indirectly given, so we have to figure out. And the keyword is that this circuit has reached steady state just before the switch changes position. Okay, so the sources are DC, therefore the steady state that we're talking about is DC steady state, where the inductor behaves like a short circuit and the capacitor behaves like an open circuit. So to figure out the initial conditions, let's consider that DC steady state circuit. Okay, solution. At t equals 0 minus, we have the following circuit. Okay. 5 amps, 10 volts, 2 ohm, and here we have 1 ohm. Okay, so this is our inductor in steady state, that is a short circuit, and the current passing through it is our initial condition, okay, IL 0 minus, which we have to figure out. Likewise, or dually, the capacitor in DC steady state is behaving like an open circuit, and the voltage that appearing across its terminals will be our initial condition. Okay, so we need IL 0 minus and VC 0 minus in order to obtain the S-domain circuit. Okay, so let's figure out IL0 minus and VC0 minus. Here, this is short circuit. Therefore, this 10 volt voltage source and this 1 ohm resistor, they are in parallel in this situation. If they are in parallel, therefore the voltage drop across the terminals of 1 ohm resistor is 10 volts. So that produces 10 amps flowing through the 1 ohm resistor. Okay, and then here we have 5 amps coming in this direction. This is open circuit, therefore all of those 5 amps should be flowing here. Okay, and then here we have 5 amp and this is 10 amp, therefore by KCL IL0 minus therefore must be 5 amps. Okay, 5 coming from here, 5 coming from here, and they produce 10 amps. Okay, as for VC0 minus, it's the voltage drop across the 2 ohm resistor plus the voltage drop across the 1 ohm resistor. So here we have plus minus 10 volts, here we have plus minus another 10 volts, so 10, 10, that makes 20 volts for the initial capacitor voltage. Okay, VC0 minus equals 20 volts. Okay, now we have the initial conditions. That means we have everything we need in order to be able to obtain the S-domain circuit. Okay, now S-domain circuit. Okay, now we're considering the circuit after T positive, therefore the switch is in top position. That means the current source is taken out of the picture, and what remains is the other stuff, and that in S-domain produces the following. Here we have the 10 volt voltage source, then we have the inductor, here we have the 1 ohm resistor, then we have the 2 ohm resistor, and here we have our capacitor. Okay, this is our time domain circuit, 2 ohm and 1 ohm, and from this time domain circuit we will obtain the S-domain circuit. So this was a 2 Henry inductor, therefore this impedance is 2S. Okay, 2S ohms, and then its initial condition is 5 amps. In S domain it can be represented by a current source connected in parallel with our impedance, and the current of that current source is initial inductor current over S. Okay, so I0 over S, and I0 is 5 amps. So this is 5 over S amps. Okay, as for this voltage source, it was a constant source in time domain. So in S domain, it's represented by its constant value over S, 10 over S volts. Okay, how about this capacitor? The capacitance was okay, 1 over 4 farads. Its impedance is 1 over SC, so that produces 4 over S ohms. Okay, 4 over S ohms. And it also has an initial condition. It could either be represented by a voltage source connected in series with this impedance, or a current source connected in parallel with the capacitor, and the current that it produces is C times V0, capacitance times the initial voltage. Now if capacitance is 1 over 4, initial voltage is 20, we just figured it out, so 20 times 1 over 4, that produces 5 amps. Okay, so this source takes care of the initial condition of the capacitor, and this source here takes care of the initial condition of the inductor. Okay, now this is a circuit that we want to solve, and what we ask for is VCT. Okay, so in this circuit we have to figure out VCS, therefore we have to figure out this voltage. Once we have VC of S, then we can transform it to time domain easily. Okay, so let's apply node voltage to solve this circuit. This is our ground node, and let me label this node as E1 and this node voltage as E2. We're going to write the node equations. Okay, we have two unknowns, E1 and E2. That means we're going to write two equations, and from those equations we will figure out E2 of S. And E2 of S is what we're looking for, because this node voltage is no other than the capacitor voltage that we are after. Okay, so let's write node equations. Node 1. Okay, so here this is our node 1. So what we will do is we will add these four currents, and by KCL that equals 0. So this current is E1 minus 10 over S divided by 2S. Okay, then we have this current which is minus 5 over S. Then we have this current which is E1 over 1, and finally that current is E1 minus E2 divided by the resistance in between, and by KCL, which holds in S domain as well, that should equal 0. Okay, so that's our first node equation. Let us put it in a nicer form. We can write 3S plus 1 2S E1 minus 1/2 E2 equals the right hand side, and the right hand side in this case is 5 times S plus 1 over S squared. Okay, so this is our first node equation. Now we're going to do the same thing to node 2, and our formulation will be over. Then we have to solve for E2 of S. Okay, writing KCL in the second node. Now we can add these three currents, this, and that, and the sum must equal 0. So we have E2 minus E1 over 2 plus this current, which is E2 over 4 over S. Okay, finally we have this current which is minus 5 amps. Okay, minus 5, that equals 0. Okay, now reorganizing the terms, we can write our second node equation as minus 1/2 E1 plus S plus 2 over 4 E2 equals 5. Okay, this is our second and last node equation. Now from these two equations we have to pull E2. So let's do that. First, using the second equation, we can write E1 in terms of E2, and then that expression we can plug in to our equation 1, and after manipulating the terms we can obtain E2 of S. Okay, so what's E1? By looking at equation 2, we see that E1 equals S plus 2 over 2 E2 minus 10. Okay, call this equation 3. Now we combine equations 1 and 3. 1 and 3, and we can write 3S plus 1 over 2S times E1, and E1 is here in terms of E2, S plus 2 over 2 E2 minus 10, and minus 1 over 2 E2 equals 5S plus 1 over S squared. Okay, and then this equation is now only in terms of E2, and that's what we're after, because E2 is the capacitor voltage. Now that equation, after some middle steps, can be written in the following, or from that equation we can obtain E2 of S in the following form. E2 equals 20 times 3s squared plus 2s plus 1, and then the denominator is s times 3s squared plus 5s plus 2. Okay, so I have skipped the middle steps, they're a little long. In the end, this is what we obtain, a rational function. Okay, and then further manipulations give us the following: 20s squared plus 40 over 3s plus 20 over 3, and the denominator in factored out form produces s plus 2 over 3, and then we have s plus 1. Okay. Now the form of E2 of t therefore will be we will have some constant term, okay, and that term is due to the voltage source. Okay, so that's the input in the time domain circuit, and we have two other terms. One is e to the minus 2t over 3, and the other is e to the minus t, and those terms has to do with the natural frequencies of the circuit. Therefore, since we know that this is coming from the input, the remaining two poles, okay, must be the natural frequencies. That is, the circuit, which we know is second order, has natural frequencies at -1 and -2/3. Okay, so all that remains to obtain E2 of t is writing E2 of s as sum of first order terms. Okay, so let's do that, and that will give us the answer. Okay, so that means E2 of s equals something over s plus something over s plus 2/3, and finally something over the last term, s plus 1. Okay, those somethings we call residues. And how we compute residues? Okay, what's K1? Well, multiply both sides with s, the denominator of this term, and then evaluate s times E2 of s at s equals 0. Okay, so if you multiply E2 with s, that will cancel with the s in the denominator, and what remains you evaluate at s equals 0. So if you plug in s equals 0, these terms disappear, so you have 20 over 3 divided by 2 over 3 times what? So that produces 10 as K1. Okay, and K2 equals, this time you multiply E2 of s by s plus 2 over 3, and if you do that, this is what you have: 20 s squared plus 40 over 3s plus 20 over 3. And then, since we're multiplying this with s plus 2 over 3, it will cancel with this term in the denominator, and denominator reduces to s times s plus 1. And then we evaluate this at s equals -2/3. Okay, and that produces -30. And finally, K3 is, we do the same thing, 40 over 3s plus 20 over 3, and then this time this term is cancelled because we're multiplying E2 of s by s plus 1, and what remains is s times s plus 2 over 3, and this is evaluated at s equals -1, and that produces 40. Okay, and now we have figured out all the residues, and we're almost done. Okay, so VCT, which we were asked for, equals E2 of t, our second node voltage, whose Laplace transform is here. And we have figured out the residues. Therefore, E2 of t equals, this produces the constant term. K1 is 10, so we have 10. And then we have minus 30 times e to the minus 2t over 3. 2t over 3. And finally, we have plus 40 times e to the minus t volts, okay, for after the switch changes position. Okay, now let's move on to our second example. Example. Okay, the circuit given is this. Again, we have a constant source, 10 volt. We have a switch, and then we have this parallel connection. The switch closes at t equals 0. Then we have a capacitor. And then this one port is connected to what we call a load. Okay, these are terminals A and B, and this voltage is labeled as V of t. Okay, and this is the load. Now the parameter values are 1 Henry, 1 ohm, and this is 1 farad. And this is the explanation for this example. The circuit, we are told, is at 0 state, meaning all the initial conditions of the dynamic components are 0. Okay, no initial inductor current, no initial capacitor voltage. Before the switch is shut, at t equals 0. Okay, we are asked to obtain the Norton equivalent seen by the load. Okay, that is Norton equivalent to the left of the terminals A and B. Okay, so we're talking about the Norton equivalent seen when looked from that side. In S domain, okay, so we have to obtain Norton equivalent S domain to solve for the load voltage V of t when the load is a 1 ohm resistor and B 1 farad capacitor. Okay. So let's therefore begin our solution. here is the solution. Let's figure out the Norton equivalent seen by the load in S domain. Okay, in time domain we cannot talk about such an equivalence because we have dynamic components. But in S domain, since the circuit is just like an LTI resistor circuit, we can talk about some Thevenin impedance, Norton current, and Thevenin voltage. Okay, here is the solution. Let's transform the circuit to S domain. Okay, and it will be quite easy because we don't have to worry about the initial conditions. We're dealing with a zero state circuit. So the dynamic components will be represented only by their impedances. Here we have the inductor resistor bank, and here we have the capacitor, and this is our terminals. Okay, A and B. Okay, now this is the voltage source in time domain. Since it's a constant source in S domain, it's just that value divided by S. So we have 10 over S volts. The impedance of the inductor is S times L, L being 1, we have simply S ohms. We directly carry the resistances to S domain, and as for the capacitor, the impedance is 1 over SC. C being 1, we have therefore 1 over S ohms. Okay. Now, for this circuit, we're going to compute the Norton equivalent. So that means we have to figure out the short circuit current, which will be our Norton current. Okay. Short circuit, and we have to figure out the Thevenin impedance seen from the pair of terminals A, B. So let's begin with computing the short circuit current. This is the circuit in S domain with the terminals shorted. So let's first compute the equivalent impedance for this parallel connection. I'm going to call it Z1 of S. Okay. So what's Z1 of S? Z1 of S is S times 1 divided by S plus 1 because they're in parallel connection, S over S plus 1. And then once Z1 of S is figured out, which is here, S over S plus 1, the short circuit current is simple to compute. Since this is shorted, this impedance has no effect. The impedance due to capacitor has no effect on the short circuit current. Short circuit current simply is the voltage, okay, of the voltage source divided by this Z1. So I short circuit is the voltage of the voltage source 10 over S divided by Z1 of S. Okay, and that's 10 S plus 1 over S squared. So this is our Norton current in our Norton equivalent circuit, amps. How about Z Thevenin? Z Thevenin equals, well, if we have the open circuit voltage, okay, which is the Thevenin voltage, then the ratio of open circuit voltage to short circuit current gives us the Thevenin impedance, okay? But there's another way. What you do is you kill all the independent sources inside the one port, and then you figure out the equivalent impedance. In this case, that seems to be a reasonable way to approach because the structure of the circuit is quite simple. Now, if you kill the source, what this killing it means replacing it with a short circuit. What we have is Z1 connected in parallel with this impedance 1 over S. Therefore, Z1 parallel with 1 over S is our Thevenin impedance. Okay. So Thevenin impedance is Z1 of S connected in parallel with 1 over S. And that equals 1 over S times Z1, which is S over S plus 1 divided by 1 over S plus S over S plus 1, and that equals S over S squared plus S plus 1. Okay. Now we have all the things that we need in order to write down the Norton equivalent circuit seen by the load. Okay, we have the Norton current and we have the Thevenin impedance. So we can now begin dealing with parts A and B. Okay, A. Now, this is the Norton equivalent circuit. Okay, this is A, this is B. This is our Z Thevenin impedance, and the Norton current is 10 S plus 1 over S square amps. Okay, and then for part A, the load is a 1 ohm resistor. So here we have a 1 ohm resistor. And then what we're after is the voltage across the terminals of the load, V of S. Okay. And it's very easy to compute using the Norton equivalent circuit. All we have to do is compute the equivalent impedance, this Thevenin impedance connected in parallel with 1 ohm, and then this current will be flowing over that equivalent impedance and generating the voltage that we're after, V of S. Okay, so V of S in this case is the current, Norton current, multiplying the equivalent impedance seen by the current source, which is Z Thevenin connected in parallel with 1 ohm. Okay, so that equals 10 S plus 1 over S squared times, okay, Z Thevenin is here, S over S squared plus S plus 1 times 1, and then we have S squared plus S plus 1 plus 1. Okay, and that equals what? 10S plus 1 over S squared times S over S squared plus 2S plus 1. Okay, and that equals what? Now, this S will cancel one of the S's here, okay? And this is S plus 1 square, therefore, one of the terms here will be cancelled by S plus 1, and what remains is 10 over S times S plus 1, which we can write as the following sum of first order terms, 10 over S minus 10 over S plus 1. So that's our V of S, okay, when the load is a 1 ohm resistor. Hence, V of T is simply the inverse Laplace transform of this, which is 10 minus 10 times e to the minus t volts. V of T equals 10 minus 10 times e to the minus t volts for T positive. Okay, now in the second situation, the load is a 1 farad capacitor. So that produces the following circuit, which we can easily solve because we have the Norton equivalent circuit. part B. Again, get Norton current, Thevenin impedance, and here we have 1/s ohms for the capacitor, because capacitance was 1 farad, and we were told that the circuit is at zero state. Therefore, we don't have to worry about the initial conditions of the dynamic components. They're all zero. Hence, the capacitor is represented solely by its impedance, which is 1/sc, and that equals 1/s. And what we're after is, again, this voltage across the terms of the load, V of S. We're going to do the same thing. This time, Z Thevenin is parallel to impedance 1/s instead of 1. Okay, V of S equals 10 S plus 1 S squared over S squared. Okay, this current will be visiting that equivalent impedance seen by the current source. And then the current times that equivalent impedance generates this voltage. Z Thevenin in parallel with 1/s. And that produces the following rational function. S squared plus 1/2s plus 1/2. Okay, now we have this, and we can again apply inverse Laplace transform techniques, and let me just directly give you the answer. V of t, the voltage, inverse Laplace transform of V of s, produces the following. We have a constant term due to this s in the denominator, and it turns out that the second order polynomial has a complex conjugate pair of roots. Therefore, we will have some oscillatory but decaying terms, and those terms turn out to be this this pair: 10 e to the minus t over 4 cosine omega t, where omega turns out to be square root of 7 over 4 t. Okay, plus 10 over square root of 7 e to the minus t over 4 times sine square root of 7 over 4t volts. Okay, for t positive.